Okay, hello student, good evening. So today we are going to discuss about a topic by the name of extrinsic semiconductor material. Okay, extrinsic semiconductor material. As we know very well, the intrinsic semiconductor material. What is intrinsic semiconductor material? Okay, so as we know, semiconductor material, intrinsic semiconductor material is nothing but it is a silicon and germanium. Silicon, germanium are these semiconductor material. Okay, so these are indirect band gap semiconductor material. So as we know very well, this intrinsic semiconductor material, it is one of the what interesting material. But the thing is that we can't realize the power of this semiconductor material. Okay, so this is what pure semiconductor material. What pure semiconductor material, pure semiconductor material. But we are unable to realize the real power of this semiconductor material, this pure semiconductor material. For that, what we need, for that, if we want to realize the power of this intrinsic semiconductor material, then for that we need what, for that we need to add what, we need to add controlled amount of impurity. Okay, we need to add controlled amount of impurity. Let us say this is my semiconductor material. Okay, so this is my silicon material, which is what, which is pure. Yes, this is my pure silicon material. So this is my pure means it is intrinsic, it is what, intrinsic material. Okay, so this is intrinsic. So but this intrinsic, it is what, it is very interesting. Okay, interesting material. But the thing is that we are unable to realize the actual power of this pure semiconductor material. For that purpose we need what, we need some doping. Okay, so we need what, we need to add, we need to what, add, we need to add controlled amount of impurity. We need to add some controlled amount. Yes, we need to add some controlled amount of impurity. Yes, controlled amount of impurity. So that is what, dopant atom. These are dopant atom. Okay, so we need to add some controlled amount of impurity, which will enhance or which will alter the characteristic of this pure semiconductor material. So then we are able to see the actual power of this semiconductor material. Okay, so when we dope some impurity with this pure semiconductor material, then it will enhance the what, it will enhance or it will alter the characteristic of this semiconductor material. Okay, so this doped semiconductor material is nothing but extrinsic semiconductor material. Extrinsic semiconductor material, with the help of this what, with the help of this we are able to fabricate various semiconductor device in this world. Okay, so as we know very well, intrinsic semiconductor material is one of the interesting material. So but we are unable to realize the actual power of this pure semiconductor material. For that purpose we need what, we need some, and we need some controlled amount of impurity. Okay, so we need to add some controlled amount of impurity. These impurity are dopant impurity, and is known as what, and it's known as dopant atom. So that may be either acceptor or donor atom. Okay, so and this doped material is nothing but, is known as what, extrinsic semiconductor material. Okay, so it is the primary reason that we are able to fabricate so many devices. Okay, so with the help of this external, with the help of this doping. Okay, so doping, for that we will see first qualitative description about this dopant atom. Okay, so let's go. So let's see, first we will see what, first dopant atom, that we will see from group fifth element. Okay, so dopant atom, so dopant, so this is my dopant atom. So let's say this is from group n type. We will see first n type dopant. Yes, dopant atom for n-type. So what we will do? So first take what? Silicon crystal, two-dimensional silicon crystal. Okay, so I am taking what? One two-dimensional silicon crystal. Okay, single crystal silicon. So this is my two-dimensional single crystal. Okay, so this is my single crystal, silicon crystal. So this is my silicon and this is my silicon. Okay, so if you see here, this silicon, what? Silicon atom, this silicon atom has how many electron? How many outermost electron? 4. Yes, every silicon atom has 4 valence electron. Yes, 4 valence electron. 4 valence electron. Yes, now it is what? This one is pure silicon material. Pure silicon material. Okay. So now here if we see it will generate. Okay. If we provide some energy for this pure semiconductor material, then it will generate the current which is unable, okay, so which is unable to run the device in proper manner. Okay, so therefore in that way we are unable to realize the actual power of this pure semiconductor material. For that, what we need to add some controlled amount of impurity. We need to add the impurity atom in controlled manner. Okay, for that, first of all we will see the n-type impurity atom, dopant atom as n-type. For that, we will take first fifth group of element. Fifth group element is like phosphorus. Yes, this is my fifth group element, and this phosphorus atom, this is my fifth group element. Okay, so in this atom, okay, so phosphorus atom which has 5 which has 5 electron in its outermost shell. How many electron is there? 5. For what? For phosphorus. Now I am going to add this phosphorus to what? To silicon material, pure silicon material. Okay, as i will as I will dope this phosphorus atom, okay, to this pure silicon material, then if you see here, just take here phosphorus. Okay, I am taking here phosphorus. So it has, out of, if you see, out of five electron, 4 electron will participate in what? Covalent bond. Okay, so they will take part in covalent bonding. Okay, so these 4 electron out of 5, and this fifth electron is remaining what? Remaining loosely bound to this phosphorus atom. Okay, so there is what? Now there is 4 electron. So this is 4. Okay, so now this octet has been completed with 8 electron. Okay, 8 electron, as we know very well, it required 8 electron to complete one octet. Okay, so to become stable. So for that purpose, if we see, the 4 electron will take part in covalent bond, and they will involve in covalent bond. Okay, so these 4 electron, and if we see, fifth electron is remaining unattached. This is loosely bound electron that is connected, that is what? From phosphorus. Okay, so this is what? This is acting as excess electron. This is my excess electron. You can see this is why this is like excess electron. Okay, so now what we are seeing here, if you see this free, if you see this excess electron, yes, this is excess electron, it required very less energy. Yes, this excess electron, by intuition we can say that this excess electron, or this excess electron, which is, or we can say this is what? Donor electron, which is loosely bound to this phosphorus atom. Okay, it required very less energy to become free, or to become free. Okay, so now if we apply very small amount of energy to this loosely bound electron, then what happen? It will get elevated to the conduction band. It will get elevated to the conduction band without creating the hole, but it left the positively charged phosphorus ion. Okay, behind it. Okay, so once we apply very small amount of energy, so if you see the what? Energy band diagram. So this is my conduction band. Here, this is my conduction band, and this is my valence band. What? This is my valence band, and this is my energy band gap. what? Energy band gap. See, energy band gap. So now see here what we are seeing. These excess electron are, this excess electron represent what? This. Okay. So this level, this level. These are my excess electron. Yes, these are my excess electron, which is loosely bound electron, and it required very less energy to become free, to become detached. Okay, to become detached from this phosphorus atom, it required very less energy. And these are my excess hole. These are my excess electron. If I will provide small amount of energy, and if I will give small temperature like about 50 degrees Celsius, then these electrons will get jump into the what? Into conduction band. These electrons will jump into the conduction band. Okay, conduction band, and left behind what? Left behind the positively charged phosphorus ion. Okay, so phosphorus ion, let's say I am applying the energy by applying the temperature about 50 degrees Celsius. 50 degrees Celsius, if you will see this is my conduction band, and this is my valence band. This is my valence band. Okay, so now what I am doing here, just okay, so just I am applying here temperature about 50 degrees Celsius. So there is what? There is a creation. If you see, there is a formation of what? There is a formation of what? Formation of positively charged ion. Positively charged ion. Okay. After applying what? After applying the temperature. After applying the temperature about 50 degrees Celsius. Okay. 50 degrees Celsius. Then there is a formation of what? Formation of positively charged ion. Okay. So these are donor energy level. Formation of donor energy level, and corresponding to that, there is a formation of what? Formation of electron in the conduction band. There is a formation of electron in the conduction band. Okay, so this is by intuition we can say that this loosely bound electron to the phosphorus required very much less energy to become free, and get elevated to the conduction band. Okay, so without creating any hole. Okay, so but instead of creating the hole, it will create the positively charged ion. Okay, positively charged ion. Okay, so now this electron, if you will see, now these electron, these are what? Excess electron. Okay, so which has jumped to this energy level. So this is my donor energy level. Okay, so there is a formation of donor energy level. Corresponding to that, there is a formation of excess, there is a formation of electron inside the conduction band. Inside the conduction band. Now if you will see here, now these electron in the conduction band are able to move throughout the crystal, and they will throughout the crystal, and they will what? They will generate the current. They will generate what? Current. Okay, so but the positively charged phosphorus ion will remain fixed within the crystal. They will remain fixed within the crystal. Okay, so therefore from here what we can say, that the impurity what? Impurity atom donate. Impurity atom donate. Okay, so somewhat we have to write up. So just here. Now from here, what you can say, that impurity atom. What is this? Impurity atom. Impurity atom. Donate what? Impurity atom donate electron to the conduction band. Electron to the conduction band. Electron to the conduction band. Okay. So impurity atom donate the electron to the conduction band, and hence it refers to as a and refers it refers to as a donor atom. So these are donor atom. Okay, donor atom. Hence this impurity atom is called as donor atom. So group fifth atom is known as donor atom, because they are donating the electron to the conduction band. Okay, and this donor atom generate the electron in the conduction band without creating the hole in the valence band. So this is the beauty about this type of material. Okay, this type of material, and this material is known as what? Is known as n-type material. Okay, n-type material. Okay, so this material is known as n-type semiconductor material. Okay, n-type semiconductor material. N-type semiconductor material. Okay, material. This donor impurity atom generate the electron in the conduction band without creating the hole in the valence band. Okay, hole in the valence band, and is called as what? Called as n-type semiconductor material, and stand for negatively charged electron. Negatively charged electron. Okay, so this is about what? This is about n-type semiconductor material. N-type semiconductor material. Okay, so everything we have seen. First we took what? First we took the phosphorus. We took what? First group fifth element. Group fifth element. Then we have seen group fifth element as phosphorus. Phosphorus has how many electron at the outermost shell? Five. Out of five, four will take part in covalent bonding. Covalent bonding, and one electron that is left, it will act as what? Excess electron. Okay, so which is very loosely bound to this phosphorus atom. Okay, so by intuition we can say that or it seems clearly that this excess electrons or loosely bound electron will what? Will take very less energy to become free and jump to the conduction band. And in this way we have provided what? Very less amount of temperature, about 50 degrees Celsius. 50 degrees Celsius. Okay, so then it become free and without creating what? Without creating hole. Instead of this, it will left what? Positively charged phosphorus. And these electrons will what? Move throughout what? Interatomic space within the crystal, and in this way it will generate the current. It will generate the sufficient amount of current. Okay, so that is able to run the device. Okay, so this is all about this n-type semiconductor material. Okay, hence these are called n-type semiconductor material, and stand for what? And stand for negatively charged electron. Okay, so now come to what? p-type semiconductor material. P-type semiconductor material. Now see here, p-type semiconductor material. p-type 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 semiconductor p-type semiconductor p-type semiconductor material. Okay, p-type semiconductor material. Okay, as like of n-type semiconductor material, we are going to see the p-type semiconductor material. Okay, so what we will do here? First you take what? First you take two-dimensional what? First you take two-dimensional single crystal silicon. What? Single crystal silicon. Here silicon. Okay, so this is my silicon, and this is also my silicon, and this is also my silicon. Okay, silicon atom I am taking only for as per our convenient ways. Okay, so that we can represent very easily. Okay, so this is my four silicon atom. Okay, so this is my single crystal silicon. So still this is what? This is pure or intrinsic semiconductor material, which is very famous. But the thing is that we are unable to realize its actual power. Okay, its actual power. When we realize the actual power, uh, only when we add some controlled amount of impurity. And as we have seen in case of n-type semiconductor material, now we are going to what? We are going to add p-type impurity. What these impurity are? So let's say from group third element. Okay, so these are my group third. From group third I am taking one element. Okay, so that is what? Let's say it is a aluminium. Okay, so aluminium is from what? Group third, and its outermost shell, the aluminium has what? How many electron in its outermost shell? Is only 3 electron. But silicon has how many? Four electron. Now I am going to add this what? I am going to add this aluminum atom from group third into what? Into the pure silicon crystal semiconductor material. Once I will add here, these all three electrons will take part in what? Take part in the covalent bond. But two of them will form the covalent bond. But third one, if I will say here my aluminum. Okay, so my aluminum here here one of the covalent bond is what empty. Okay, one of the covalent bond will appear as what empty, will appear as empty, because here is what, here is empty, here this one is empty space. Okay, so I can represent it as a empty space position. Okay, so one empty space position is there. These two electrons, if I will say, the aluminum has three electrons. So but out of that three electron, there is one electron which is what, which is hole. Okay, so it's my excess hole. I can represent it as a excess hole. Excess hole, this is my excess hole. Okay, so this is my excess hole. So now see here, see here, this is my excess hole. Okay, so here one covalent bond, it is what it is, it is just appearing as a empty space. It's not a covalent bond. Because of what? Because of what? This excess hole. Okay, so there is no, there is no electron. Okay, so it has only three electron in its outermost shell. Okay, so because of deficiency of one electron. Okay, so this covalent bond is appeared as what, as what, empty space, empty space. Now if if an electron, what I am saying, just listen, if an electron were to occupy this empty state, then its energy. Okay, so then its energy would have to be greater than, what, greater than valence band energy. I am just taking the assumption. Okay, so we are just taking the assumption that if there is some electron. Okay, so some electron, if that electron want to occupy this empty space position, then its energy would have to be greater than the energy of valence, what, energy of valence electron in valence band. Okay, so we are just taking the assumption. Since what, since the energy state of what, energy state of, I'm taking here aluminum, since the energy state of aluminum atom would be what, would be now negative. This is all assumption. Okay, so this is all assumption. And if at all, if you see, however an electron, if however an electron occupy this empty position. Okay, empty position does not have what, does not have sufficient amount of energy. Okay, so a sufficient amount of energy, an electron occupying. Okay, so however an electron occupying this empty space position does not have sufficient energy to get into the conduction band, okay, so to get into the conduction band, it does not have that much sufficient amount of energy. So therefore its energy is far less. So I am saying that, okay, so this electron, let's say this is some electron. Okay, so however this electron occupy this empty position does not have sufficient amount of energy to jump into the conduction band, this is my valence band. Okay, to jump into the conduction band, it does not have that much sufficient amount of energy. So therefore its energy is far less than that of the conduction band energy. Okay, so now conduction band energy. So now we will see what, so see here, this is my, now this is my conduction band, and this is my valence band. Okay, so conduction band, valence band. Now valence band, this excess hole represent what, these excess hole are this. Okay, so just above the edge of the valence band, these are my excess hole. What, excess hole, these are my excess hole. Yes, these are my excess hole. Now see, excess hole. So therefore let us say, so the valence electron, so now everything by assumption we have seen. Okay, so now we are taking the reality, what is happening in real. Okay, so if we provide some amount of energy, small amount of energy, by providing small amount of energy, the electron that is available in the valence band may get the small amount of energy. Okay, so and they will move. Okay, so once the valence band electron get the small amount of energy, amount of energy, and they will jump. Okay, so they will move about the crystal. Okay, so they will move about the crystal. Let us say this is valence band and some of the electron is there. Okay, so there is electron. Let's say these are the electron, and I have provided small amount of energy about what T is equal to 50 degrees Celsius in the form of temperature. Okay, so I am giving small amount of temperature and I am applying small amount of energy. Now these electrons which are available in the valence band may get small amount of energy, and they will move about the crystal. Okay, so they will move about the crystal, and the empty space position which is associated with the aluminum atom, will get occupied by this what will get occupied by this electron. Okay, by this electron then there is a electron. So then there is electron which will vacate their position. Okay, so there is electron because this is electron in the valence band. Okay, once it will get into this excess energy state of hole. Okay, then there is a hole remaining, then this next electron will jump this hole, and there is a creation of empty space. Okay, so then after that this electron will jump like this hole will move like this. Okay, so hole will move like this. Okay, so now see here, now see the creation of this hole, creation of this empty space in the valence band can be thought as a whole. So therefore we can say that the whole is moving throughout the crystal, throughout the interatomic space within the crystal, and generating the current. Whereas if you see, whereas the atom, this aluminium atom. Okay, so aluminium atom, and it will leave the positive negatively charged aluminium atom, which is fixed within the silicon crystal. Okay, so what we have done, we just have applied a small amount of energy through which this valence electron get the small amount of energy and get and will move throughout the crystal through the interatomic space. And here the empty space position which is associated with the aluminum will occupy this electron, means it is accepting this electron, and it will become negatively charged. Okay, so negatively charged. So therefore once it will occupy this vacant space. Okay, this access hole, then it will leave behind what it will leave behind a vacant space in the valence band, and that vacant space will be filled by another electron, and in this way this vacated place will get generated in the valence band. Okay, so which can be thought as a whole. Now here, from here, what we can say that the impurity atom accept the electron from the valence band. Impurity atom accept the electron from the valence band. Hence there is a formation of if you see here, there is a formation of acceptor energy level. So this is my conduction band and this is my valence band. Okay, so these are negatively charged aluminum atom. So aluminum atom. So therefore, the impurity atom from the third group of element, will accept the electron from the valence band and there is a, due to which there is a formation of acceptor energy level. Corresponding to that, there is a formation of hole within the valence band. Okay, so valence band, and hence this impurity atom is known as acceptor impurity atom. So this impurity atom from the group third element is known as acceptor impurity atom. And this hole, now see here, this hole will move throughout the crystal. Okay, so through the interatomic space within the crystal, within the crystal, whereas the negatively charged aluminum atom will be remains fixed within the crystal. And we can say that these accepted impurity atom, what these acceptor impurity atom generate the hole within the valence band without the creation of electron in the conduction band. This is the beauty about about this third group of element. Okay, so now, and this material is referred to as p type semiconductor material. P-type semiconductor material. So this is my P-type, P-type semiconductor material. Okay. So this is my P-type semiconductor material. P stand for positively charged hole. So this is about extrinsic material. Okay. So extrinsic material. Okay. So we have seen. Okay. So we have seen all these dopant atom, how we are doping, how we are doing the doping in controlled manner, and we are seeing the result. Okay, so powerful result, so which are able to run the device in very well mannered. Okay, so this is actually the primary reason to fabricate various device. Otherwise it is not possible at all without extrinsic semiconductor material. Okay, what is extrinsic semiconductor material? Is nothing but is a material. It is what extrinsic semiconductor material. It is actually a doped semiconductor material through which we can realize the actual power of pure semiconductor material. So there is a different type of doping. Okay, so that we are doing in controlled manner. Okay, so that is what, like n type impurity and p type impurity from group fifth and group third. Okay, group fifth and group third. From fifth we are getting the n-type semiconductor material, and group third we are getting the p-type semiconductor material. And in this way we are playing with this device and fabricating various semiconductor device. Okay, so this is all about extrinsic semiconductor material. Why we need it? To fulfill or to realize the actual power of semiconductor material. Okay, so why? Because the intrinsic semiconductor material, we are able to generate a small amount of current that is unable to show the actual realization of this semiconductor device. Okay, so for that purpose we have to go for extrinsic semiconductor material. Okay, so this is all about this topic, extrinsic semiconductor material. Okay, so thank you very much.